I appreciate your indulgence in watching the steps that follow. We're talking about a GC triple here, as the picture shows. The steps for the optimization assistant are the same with an LC triple as they are with a GC triple. One small difference is that with an LC triple we're trying to optimize both the fragmenter and collision energy, where in the GC triple it's often just focused on the collision energy. So if you follow along with the steps, you should be able to create the set of experiments which end up showing you the optimum conditions. Thank you for your indulgence. Hello. I'd like to talk about a tool which helps you optimize the conditions for your MRM transitions. Now, there's a number of ways to go about this process. One, for example, is to sit in front of the instrument, infuse a compound, and then you can optimize your fragmenter, find that correct, and then move on and do your collision energy. That can be very effective. What I'll show you here is a more automated way to run a number of samples by injection to try to accomplish that same goal. Now, before I get started, let me point out that if you already know your MRM transitions, you can use the same methodology to run through a set of permutations, specifically your collision energy and fragmenter voltages, to optimize your MRM transitions. In the case that I'm going to talk about here, I'm going to back up from that problem and assume that you just know your precursor ion for the compounds that you're interested in, and you really need to discover the product ions and then optimize the conditions for those product ions, ending up, of course, with the MRM transitions. So let me go through an overview of the steps in the process. The first step in the process is to create the acquisition method with the product ion scan. Now this means going with the acquisition subsystem, setting up your product ion scan. Now in the product ion scan, you are allowed within one time segment 4 different product ion scans. And in the example that I have 4 compounds, so there's a 4 product ion scan cycle. Now, once I have this method created, I can then use the tool, which I'll spend most of this time discussing, to create a work list with associated methods, each method varying the set of parameters, collision energy and fragmenter voltage. The next step, once I've got that set of methods and the associated work list, is to actually run that work list, that controlled set of experiments. I'm going to run those on the instrument, creating a set of data files. And the next step, which again I'll spend a bit of time on, is how to load those results into quantitative analysis and qual to determine what is the optimum conditions to give me the greatest sensitivity. And once I've got that information from my product ion scans, I could then go back and use the values for collision energy and fragmenter to create an optimized MRM acquisition method, as discussed previously. That's my goal, for each compound to produce transitions with associated conditions that would give me the highest sensitivity. Let's go through this undocumented feature, and I'll show you how tactically you can execute this. First, you need to go down into the binaries, which are located where you installed the application: Program Files, Agilent, Mass Hunter, Workstation Quant Bin. And if you look at the type application, you'll find a executable called ACMET-Opt Assistant, Acquisition Method Optimization Assistant. And if you start that executable, you will see the steps here that I'm going to go through. The first step is to open the template. Basically, if I have already run, which I must have, the method, or a data file collected using that method, I will have stored in that data file or method the acquisition information, including the mass spec method, which is what I'm going to apply this tool to. Now, it's stored in a file called 192_1.xml. That contains the mass spec part of the acquisition method. I will use that as my template. And you can see from looking at the information stored in this hierarchy that there is a scan segment here, and within that scan segment you can see that there is the definition of the scan. In other words, the precursor ion is 271 and it's scanning from 100 to 320, and here's another part of that cycle, 279, again scanning from 100 to 320. So there are 4 of these product ion scans defined in this method. The next step is that I need to actually define what the set points are that I'm going to vary. So in the edit parameters step, I'm going to pick a set of collision energies, and I'm also going to pick a set of fragmenter set points. I'm going to vary them from 120 to 140. I'm going to vary the collision energy from 10 to 35 in steps of 5. Now, I will now generate the methods and the work list, which I can visually inspect here. You'll notice that the names that are given are very descriptive of the conditions. But if I look at collision energy 10 and fragmenter 140 and inspect this method, you'll see that it looks quite similar to the product ion scans for the 4 compounds that I had previously looked at, except that the fragmenter and the collision energies for all these compounds have been set at 10 and 140. And you'd see the same behavior in any of the other methods that have been created. So to repeat, a work list has been created which points to the various permutations of this method. The last step is that I will save these methods to an output directory, and I will just put them at the top here of my C directory and create a folder. I'll call it opti product ion scan method. Now I've saved all of the methods and the work list to that file, and I'm about to proceed over to acquisition to run those samples. All right, now that I've saved those methods, let's take a look and inspect and see what I've got. I'm going to go over to that directory, and I'll see that I have a work list and a set of methods. The next step that I need to accomplish, if I go back to the process, is I need to run that work list and create a set of data files using those methods. So I'm going to go back to the acquisition subsystem in front of the instrument, and I'm going to take with me the Excel spreadsheet that I can cut and paste into the work list. And as you'll see in a moment, the spreadsheet has in it pointers to the method that was created that varied the set points, and also defines the data file that will be created. Now this is the default layout for the work list. The columns need to match up in the correct order, and you can cut and paste this into your work list for the sample name, the method, the data file, and the sample type. Run that work list, and you will end up with a set of data files. Next section, after running the controlled experiment set and collecting the data files, is to go in and analyze those results. That will be done in quant using the semi-quant feature of just integrating the areas and then inspecting those areas to figure out the optimum conditions. So let's go over and see how that works. Here is the data that was collected by running the series of experiments. Here is the work list that I copied into the acquisition application, and it ended up producing a set of data files which are marked with the collision energy and the fragmenter voltage in the data file name as well as the sample name. So what I've gone ahead and already done is, in Batch at a Glance, I've created a batch and I've added these samples into the batch. What I need next is a method, and I've already added in 3 compounds and their transitions. I can see that those compounds actually are extracting ions that are real by looking and observing the graphics below, which show me the spectrum and the extracted ions for each compound. Now, the next logical question is, how did I figure out what the precursor ion and the product ion was? Now, I've already mentioned that I knew the precursor ion from the acquisition method, so I already know the precursor ion for each compound. How did I figure out the target ion and also the qualifier ion that I'm using to monitor these responses? Well, I did go over to qual, and if you use qual, you will see spectra that are associated with each product ion scan. So here's 271, 279, 285, and then finally 311. And I can look at these spectra that are generated from traversing the chromatogram and then pick off ions that I want to monitor for their responses in the matrix of collision energy and fragmenter settings. Let's go through the steps to create another compound in this method so that I can observe the responses. I'm going to go and create a new compound row from the manual setup tasks. Now I know that the compound name is sulfa dimethoxine. It's in time segment 1. There's only one time segment. It's a product ion scan type. So I will choose product ion scan. I'll call it a target ion. And I already know that the precursor ion is 311. And I've determined that the product ion that I want to monitor is 155.8. Now if I look at the graphics down here, I can see I've actually got a signal for the target. But if I go to the retention time, I actually want to get the retention time a little bit closer to the middle of the window. So I'll call it 3.2. So I'll move down here to the retention time setup. And for this compound, I'll call that retention time 3.2. And now we've got the target in the middle of the extraction. Let's monitor a couple of more signals beyond just the one transition. Because I have a product ion scan, I could monitor several ions. So what I'm going to do in order to achieve that goal with this compound here is I'm going to add a qualifier ion. So I'm going to add a qualifier row from the manual setup tasks. And I'll pick an ion 108. I'll just give it a relative response of 20, uncertainty of 50. And if I look at the qualifier ratio here, I can see that there actually is a signal which appears. And notice that I can use the qualifiers to monitor as many ions in the product ion scan as I'm interested in, because when I go back to apply this method and use quantitation, you'll see those ions appear and the areas will be extracted and then integrated so I can see the responses of those transitions. I noticed an issue that when I went to validate the method, that it warned me that I'm missing the calibration table for the compound that I just added. So what I need to do is I need to add a new calibration level, and In reality, I'm not doing calibration, I'm doing semi-quant. But for the sake of validating the method, I'm just going to put level 1 and concentration 100 in. And then I will apply the method to the rest of the batch and do the integration. So now that I'm back in batch at a glance, I'm not going to do the full analysis or full quantitation. What I'm going to do is I will analyze and then integrate the batch. That will give me the areas for all the transitions that I've set up. For example, in this case, I've got the 279, and I'm going to be monitoring the transition for the target. I'm going to be monitoring the transition for the qualifier. The way I'm using this in this optimization experiment is that I am monitoring those areas. And after the integration is through, I'll show you how to look at each compound individually, look at the transitions for that compound, and then pick the combination of the collision energy and the fragmenter that would be optimum, give you the optimum response, the optimum sensitivity based on this set of experiments. As I can see here, I've got actual target responses and I've got the qualifier responses down here, and I can see them graphically as well as my spectral transitions with the precursor ion marked with the blue here and the transitions showing up as ions in my spectra. So as this comes to a conclusion, I'll take a look at the first compound, sulfmethoxide, and then see the area responses in the single compound view. I could look at it in the multi-compound view, but I think it's actually easier to determine this and pick these values off that I would go back to the acquisition method. So here I am looking at my first compound, and I'm going to simply sort on the area here. Now I could go over to Excel and graph these responses, but I think it's actually easy enough to see just by looking at the responses from the table. So for this compound, there's some difference, the top being collision energy 35 and fragmenter 125. If I pick another compound and I look at those ions that have been extracted, I can see that sorting on this compound, there is quite a bit of difference in terms of the settings of the collision energy. In this case, 15 for the collision energy and fragmenter of 140 has given me the top response. Yet notice for the qualifier transition, 179 goes to 124. If I sort on that, getting the highest response at the top, you get a different combination. So you could take these transitions, and in the acquisition method that you're going to create for MRM, to get the most sensitive response, you could assign that collision energy and that fragmenter for that particular transition. So looking at the whole picture of all the ions, I can easily see from the spreadsheet approach and confirm by looking at the ions in the graphics and the spectra what are the optimum conditions using this product ion scan and extracted ion quantitation method. I can see the areas that give me the best combination, and I hope that is useful for you in optimizing your compounds. Thank you very much. Again, I would like to show you a more advanced use of the acquisition method optimization. Typically, we are just satisfied with optimizing the collision energy and the fragmenter voltage. I will show you how to go beyond that and optimize another parameter, the VCAP, sometimes called the CapX voltage. Let me show you how that looks. As we've seen before, I can open the acquisition method with a triple. And in this case, I'm looking at, for the source parameters in this time segment, I'm looking at the pos polarity value, which is set at 4,000. And I would like to change that to different settings to see the result of the sensitivity. I go to Edit Parameters, and now I see past the collision energy and fragmenter, I've also got the VCAP set points, which are iterated through these values. And again, I can go and generate that set of methods, and you'll notice that the naming is now collision energy, fragmenter, and then I've got the VCAP settings, as I've said, up here. I go ahead and create the work list, generate the methods that are associated with that work list, and then run them, and I've got a set that I can analyze as previously shown. I think you're going to ask, how did it happen that the optimization assistant got the extra choice of iterating the VCAP voltage? So let me show you how that works. I'm going to go to the configuration file, the XML configuration file that's associated with the application, and I'll open that with Notepad. Now looking at Notepad, if I zoom in here, I'll see the configuration for the collision energy. I will see the configuration for the fragmenter voltage. And what I've done here is I've added in another choice, the VCAP choice, and given it the defaults as you saw right in the user interface. Now, the point of setting this up is this program will use this expression right here that will go in within what is called an XPath expression and modify the acquisition triple method that is an XML document. And in this case, the path to that change is shown here: time segments, source parameters, pos polarity value, and I make sure that it's only going to edit the VCAP part of the positive polarity value, and that's what will be iterated in the resulting methods. So that is a generalized approach to optimizing basically any parameter that is in the acquisition method. Thank you very much for your attention.